All right, this is a screencast of Chapter 16 of this Applied Statistical Analysis course. And we're going to deal in this chapter with categorical predictors in linear regression models, which then turn into ANOVA models. And I have a few missing screencasts from a few of the previous chapters, and I'm back. So you can go down to Chapter 16 to grab the supplemental materials, which include a couple figures that are created in this chapter plus this walkthrough. So save this in someplace convenient. And I have saved it and loaded it. Also note that the course book is available at the top of this page. The link is in the description under this link right here. So we have previously spent just a little time thinking about categorical predictors. We've done some examples, and most of them, but I don't know if all of them previously have been binary. So if you have a binary predictor, it's pretty easy to think about. There's, either you have it or you don't have it, and it sort of turns into an intercept. But what if you have multiple levels of predictors? We want to talk about today how the R regression handles that, and different ways that you can specify it to make it adapt more closely to your particular design. We're going to be using these. I think these are the libraries that are used at least a little bit. The CAR library, the Agricole, Mass, Bayes factor, and Bioplot. So let's say you have, here's a set of sort of degrees or specialties: advertising, business, and certification. And I've put these in alphabetical order, A, B, C, just for convenience. And if we look at specialty, it's got 3 levels that happen to, and levels are always organized in alphabetical order. So the first level is advertising, the next is business, the third is certification. And let's say we've recorded a bunch of people who have this specialization and what their starting salaries were or what their hourly salaries are or something like that, and here's the numbers. We can look at this and see that the mean is 37, maybe it's $37,000 a year as a mean starting salary. But we could aggregate across different specialties and see that, oh, there's differences. Advertising is in the middle, business is highest, and certification is lowest. And so we know how to do this aggregate, but previously we could say, well, can we predict salary based on specialty? So the model might look sort of like this, just salary tilde specialty, and we can see the results indicate, well, this is kind of strange now. We have an intercept, and then it's business and certification. We don't have advertising, but the mean for advertising is the same as the intercept, but the mean for business is not the same as business. And if you look closely, you'll see that 18.6 plus 34.2 is equal to 52.8. Similarly, certification is 10.2 lower than this. 34.2 minus 10.2 is 24. So by default, what it does is it takes the first level and sort of zeroes it out and makes the mean the intercept with respect to the first level, and then the others are coded with respect to that. So this is called treatment coding. And really, in order to represent a categorical variable, you can't just give it numbers. You have to give it a matrix of numbers that represent an independent or orthogonal set of values to allow you to do this. But there are many different ways you could represent these values independently in a design matrix. Notice that if we add 0 to this, we get the actual values. So we remove the intercept and they all get coded with respect to their own level, and so this is sort of like saying each has its own intercept. To find out the way it's coded in terms of a design matrix, we can look at contrast. So any factor automatically gets a set of contrasts created based on it. And here, so if you look at contrast, this is what it looks like. So really, if we go back up here, we had an intercept of 34, and then we had these two other values, and these two other values are represented by business and certification. So here, advertising sort of indicates a level of 0 gets added to the intercept. Business gets this business factor, and certification gets this certification factor. So this is called treatment coding because each of these variables just picks out a single one of your input variables, ignoring the first one, and the first one then takes the default value of 0. You know, sort of like saying there's an intercept and this one's 0 away from it. So it pins down the intercept at the mean of this, and then this gets to be 0 away from it. So if you look at the contrasts, I can create with the function contr.treatment a set of treatment contrasts by giving it the number I want. So you can see that this matrix here is identical to this except without the names. And if instead of giving it numbers, I give it named levels, 3 named levels, like the levels of specialty, it creates an identical to this. So this is exactly what is embedded within the factor. So this specialty contrasts were created way up here when I made the factor. And you can, this looks a little weird, but you can set the contrast of a factor using this sort of syntax. You pull the contrast out, and it's weird because it's on the left side of the assignment, but this is the same way as you change like row names and column names and things like that. So instead of doing it alone, I can set this equal to it, and you can see, well, it didn't change because I set it equal to the thing it was already, but this is how you change the contrast. So you can create a factor, and you can then change the contrast. There may be a way to specify the contrast within a factor command as well, but this is sort of the easiest way to do it. So this isn't the only set of contrasts. There's many different types of contrasts that are used, and what you should think about is if maybe you have a design that it makes sense, that these contrasts make sense. For example, maybe your first level is a control level, and you want everything coded with respect to the control, and then this makes a lot of sense. But maybe you have some other type of arrangement of levels of factors that this doesn't make sense. And so you can create, either using a canned contrast function, or even on your own if you're if you want to put in the time to figure out the best contrast, a set of specific contrasts to represent the levels of your variable that is most informative for the test you want to do. And so if you have a set that's informative for the test you want to do, these are essentially planned contrasts, and you can get you can test the significance of these directly from the ANOVA or the regression that you end up creating. So treatment contrast isn't the only way. SAS does treatment coding in a different way, and so if you want to be consistent with SAS, you can set them to contr.sas, and you can see that it looks very similar, but the last one, not the first one, gets 0 coded. So everything is with respect to the last element, not the first element. I can reset now like this, and now you can see my intercept is 24, whereas before it was 34.2. And relative to the mean of the last one, and everything gets coded with respect to that. Advertising and business, but I don't get a certification level. Advertising is 10.2 more than certification, and business is 28.8 more than certification. So you can, if you can figure out a set of contrasts that best represent your design, you can always set your factor to have that contrast, and then the test you run, the linear regression test, will test the specific contrast, which might be really what you want. Note that if I add 0 to this, I get the original values back. It doesn't. Then the contrast, the way I did the contrast, doesn't matter. It'll give me the absolute means in this case again. There's other ways. Helmert is another popular one. I think that I read that this is maybe reverse Helmert coding instead of true Helmert coding that R uses, but Helmert coding, let's see, if we look at mean of salary, it's 37. Let's just keep that in mind. So Helmert coding is a little weird, but it allows us to sort of see where things start changing. If you have multiple factors that are in order, this allows you to have a set of contrasts that sort of code that ordinal change. So if you've got, you're waiting for growth to take off and it doesn't grow and it doesn't grow and it doesn't grow, and then all of a sudden it grows, you could use this because, let's see, the first level compares A to B, the second level compares A and B to C, and so on. The third level will keep going. If I do 5, you can see the third level does the first 3 to the fourth one does the first 4 to the fifth one, and so on. So you can see the pattern here allows you to, in each case, test whether the last thing is different than everything previous. And so this would allow you to, if you have a categorical variable that's still ordinal, figure out where a specific change takes place. So I can set it equal to, the contrast especially equal to the Helmert coding of that, and then just look at the summary of this. Now this doesn't completely make sense because these aren't really ordinal, but now you see the intercept. The other thing that the Helmert coding does, the intercept, actually is the mean of the entire set. Remember, 37 was the mean of the mean salary overall. And now you say, okay, here's the mean salary overall. And that's kind of handy. It doesn't link it to any specific element. But then specialty 1 says, is there a difference between 1 and 2? And indeed there is. And then it says, specialty 2, is there a difference between specialty 3 and the average of specialty 1 and 2? And indeed there is there as well. So this is just another way of doing the coding, and if your design makes sense, then that's a reasonable thing to do. If we look at this, we'll notice we talked a few chapters back about orthogonality and correlation, how those are good to have. You can see that any pairing here are going to be, if you do a cross product like this to this, everything below this is going to cancel out. So this is a positive and a negative times 2 negatives. These are always going to cancel out and be 0. So every pairing of this is going to be orthogonal. And if I look at the correlation here, it's a little harder to intuit, but the correlations between any pairing are 0 as well. So we have, for Helmert, along with the treatment coding, we've got orthogonal and uncorrelated codings for these sort of dummy variables that we're creating to represent the different levels of a categorical factor. Helmert coding is a little easier to see if you have something where you're looking for a change. So here's 12 months of the year, and I'm just organizing them in order, January through December, and we see levels, and around July it increases. So you might expect to see a significant effect here, but not elsewhere. So if I do contrast dot Helmert for the levels of months, then and set that equal to months, I can do a regression of value times months. But and now, well, first of all, again, this is the average overall, 4.04. But now months should be the difference between month 1 and month 2, or some sort of half of the difference between month 1 and month 2, and that doesn't seem right because month 1 and month 2 were very small. Something's wrong here. And it's hard to see because it renames all your factors. Well, let's look at what happened. If we look at contrast of months, we can see, oh, this is strange. What it's putting them in alphabetical order. And if we look at levels of months, you can see that the levels are in alphabetical order. So even though a factor is categorical, it has an order, and sometimes it matters, and this is one of the cases where it matters. So we want to make sure the factor is in the order we care about, and R doesn't know that you wanted it in the specific order that you gave it. It might seem like a reasonable thing to do, but very typically these data won't be in the order that you want them in. They'll just be in a random order, and so it defaults by putting them in alphabetical order because it's sort of arbitrary. If you don't want them in an alphabetical order, you have to specify that specifically. So here's some code to do that. Instead of a factor, I'm just going to make a vector of those names and then turn months into a factor, giving the levels, which are this. So I sort of give months.0 twice. Now if I look at levels of months, oops, you see that they're no longer in alphabetical order. And I can now do this, right? And we can see that, again, the intercept is the average for everything. That's nice. Here, there was a 0.1 difference between January and February, and this month is half of that difference. You can see it's small, 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 and then it gets bigger. It starts getting bigger here and remains bigger for a while. So you can sort of identify where the change happens in this ordinal level contrasts. So this would be useful for identifying sort of maybe the location of a piecemeal, a piecewise regression or something like that, where you have two pieces that you want to allow to change over time. I guess we could look at the summary here and see what would happen. I mean, there's only one. I don't think summary is going to do any good because we only have one value per level. So we can't really do any statistics on this because we only have one observation for level, but we can still estimate all the parameters. Okay, next, within the mass library, there's something that's sort of related to Helmert coding called successive difference coding. So if you load the mass, it's available in contour.sdiff. And it looks kind of weird. Remember, this would be the first argument, this would be the second, and you see that they add up to 0, and you can, we can also see, are they correlated? They're actually slightly correlated, so they're no longer uncorrelated. But if you, and I'm not sure if they're even orthogonal anymore. We can try that. Contour.sdiff 3, and they're no longer uncorrelated or orthogonal. So we can sacrifice that but there's a benefit here because successive difference coding now codes each element with respect to where a change happens. So it's no longer coding one thing compared to everything previous, but it's comparing one thing to each thing to its previous thing. So I can set the contrast of months equal to this, and look here, you can see that, okay, the average is 4. We have a +1 difference, then a -0.1 difference, then a +0.3, a -0.4, a +0.3, and then a +2.8. So now you can see that this is where a big transition happens. And then here we also have big transitions after that point. I could do this successive difference for the specialty, but it doesn't quite make sense anymore. But it will name them so. I have the intercept, which is the average overall, and then I'll say specialty to advertising and certification to business. And if I'm not, and I could test each of these individually. I could, if I did summary of this, you can see that we've got a statistical test of business versus advertising and a statistical test of certification versus business. And by analogy, you can't really know without doing the test whether certification versus advertising is significantly different, but we have two of the comparisons, of the pairwise comparisons here. Which of those are the ones you're interested in might be really handy. Especially if this is like a time series, you may not really care if the first is different from the last, if you can tell the first is different from the second and the second is different from the third. All right, so another one which sometimes used is called sum to zero or deviation coding. This is available in the contour.sum function, and again, this is just a slightly different way of doing it. You can see that the first is compared to the last here, and then the second is compared to the last. So it's a little different than treatment coding, but not too much different. Notice if you multiply this by this, they will not be orthogonal because we'll have a +1 here, and these will cancel out. And I'm guessing, I don't know if they'll be correlated. They are correlated with one another too. So they're neither uncorrelated nor orthogonal. But it codes these things with respect to differences with a specific one. So in some ways, it's not too different than treatment coding. But here again, but now we've got, instead of in treatment coding, the intercept will be the first level. Now the intercept is the grand mean of the whole system, and then we've coded these two other things with respect to differences between groups. And the only problem is then you've got to figure out what this means. So the negative 2.8 means that specialty 1, which was advertising, is 2.8 less than this. So if you want to get advertising's value of 34.2, you subtract 2.8 from this. And if you want to get business's value of 52.8, you add 15.8 to this. And then you can do that for all but the last one. And then the last one is just the reverse of all of these. You take this and you subtract all these from it. So you would add 2.8 and subtract 15.8, and you'd get 24, which is the level for advertising. So this is a little hard to interpret, but it's nice that because it leaves the intercept as the grand mean, and everything else gets coded with respect to one another. And these are well, everything else gets coded with respect to the mean. So this is how far away from the mean this is and how far away from the mean that is. And that sort of makes sense from a variable selection perspective, because you might say, well, if it's not different from the mean of this, then it's really best just to treat it as the mean. Okay, so I'm going to create two different specialties. They look the same. Oh, notice that when I assign specialties, when I assign contrasts, if you just print it out, it will display what those are. By default, it won't, but if I assign it, it'll show it. So I can see that these have two different sets of contrasts for the same variable. And I can do a linear model of either one. And if I want to do an ANOVA test, we've done this before, to test whether this whole thing matters with respect to the intercept alone, I can put this in an ANOVA function. And you can see that these produce exactly the same results. So in some sense, in many cases, the particular way you do the contrasts don't matter if you're just interested in sort of ANOVA. Does specialty matter at all? Where it matters is when you want to ask questions of, is specialty 1 different from specialty 2, or things like that. So this is a standard way of doing it. Now there's a shortcut to doing this. Instead of putting ANOVA inside LM inside of ANOVA, you can shortcut this with AOV. And so this stands for ANOVA, but it's sort of a factorial ANOVA or a one-way ANOVA function. And you can see that although these are slightly different, the summary of AOV gives me this output, and the summary of the ANOVA of ln gets me this output, and they are almost the same, although this rounds off to one fewer significant digits than this does. But otherwise, the test ends up being the same. This gives me a little, these numbers look different, but they're the same. This is just giving me more significant digits. So oftentimes when we want to do what we call an ANOVA, which is especially a one-way ANOVA, which is testing whether different categorical levels of a category impact an outcome variable, we use this. And you can put it in a summary to get the statistical test related to it. And again, this will only give you whether it matters at all, and we'd have to go into the contrasts or the LM of this to get more details if we want to do those types of tests. Okay, so let's look at this on another data set. So we've looked at the tooth growth data before, and we see that if we treat dose as a continuous variable, it has a relationship with the amount of tooth growth. But maybe we look at this and say, well, if I look at this, it doesn't really look linear to me. It looks like a big jump and then a smaller jump. So that violates one of my assumptions. So maybe what I want to do is just model each of these as different levels of a factor. So there's 3 different levels, and I don't really care that they're in order or anything, or that it's the same difference. I want to see if, I want to be able to tell if this differs from this and this differs from this. Well, that's not too difficult to do. If we look at the means, we can see it goes from 10.6 to 19.7 to 26. With the overall Grammy is 18.8, so we'll pay attention to 18.8. All I need to do is create a new variable, I'll call it dosage, that that sort of what's called coerces dose, which is continuous variable, into a factor. And you only really want to do this if you have a limited number of doses. If doses was, a continuous variable and it had 100 different levels, this doesn't make sense. But if it's a designed independent variable, this is a legitimate thing to do, because it may make, then you don't have to rely on the assumption of a linear change. So now if I use dosage instead of dose and look at the summary, now this should look familiar. I've got the intercept of 10.6. If we go up here, that's this level, and then this should be about 9.1 higher, and you can see that this is 9.1 and this is 15.5, which is this is about 15 higher than the lowest level. Each of these is now, we can say, this would be a planned comparison. Each of these is significantly different than the baseline of 0.5. And of course we could have had a baseline of 0, which would have made even more sense to be our zero dosage or a controlled dosage level. But I may want to try different contrasts. Here are the contrasts that are being used. What if I wanted successive difference coding? So this doesn't make a lot of sense, but now I'm comparing 1 to 0.5 and 2 to 1. So I can do this one, and now instead I've got, now the intercept becomes the grand mean, which is nice. It says overall, if you didn't know anything about dosage, you'd expect about 18.8 millimeters growth. There's a 9.13 difference between dosage 1 and dosage 0.5, and a 6.3 difference between dosage 2 and dosage 1. And so this is a planned comparison that asks a very specific question. Does giving a dosage of 2 benefit you over giving you a dosage of 1? And it looks higher, but we don't know if that's significant. And this tells you that it's significantly higher. It didn't happen just by chance. It's very unlikely to happen just by chance. So organizing your contrast in a way that maps onto your hypotheses can make testing these very easy. You could have done this Helmert coding as well, or reverse Helmert coding. Again, this is a little different. And now we again see these three. Now this is harder to interpret. So if you're messing with dosages, if you're messing with contrast, you really have to think carefully about what these levels mean. And again, this is 18, and this is going to be sort of the difference between the first two, and that's significant. And this is going to be the difference between the third one and the first two. So this versus these two is also different. And I can verify this by picking these out and seeing that, these values that it comes up with are calculated just this way. The grand mean, the difference between 2 and 1 divided by 2 because it's twice as big, and here is the third one minus the mean of 1 and 2 divided by, but it's divided by 3. So that's how it's calculated. That's how these values are calculated. So it can be difficult to interpret them unless you know this calculation. Okay, so those are examples of how factors within R and within any linear regression need to be coded in terms of some set of what are called dummy variables, some set of vectors, and we use n-1 vectors to represent n levels of a factor. But there's a lot of different ways to do that. If you're doing just a standard ANOVA, it may not really matter. So when I showed you before, we can do either an LM of something. We'll reset specialty to its contrast, to its treatment coding, and this, if we look at the summary of the LM, we can see. Let's see, interpreting this, it says that advertising is different from 0 at 32. Business is different from advertising, but specialty is not different from advertising. This would be interpreting this system as a set of linear model. But if I instead gave it ANOVA, this asks, does specialty matter so it says, here's specialty versus the intercept only. Now this test is going to be the same as this test up here, which is comparing the whole thing to the intercept only model. But again, instead of doing ANOVA of LM, I can do AOV. And if I look at the model here, it gives me sum of squares and things like that end up being the basis for calculating these things. But if I do a summary of this model, or just a summary of AOV, I get the same tests out. And this, again, just like the ANOVA of the LM, the summary of the AOV gives me this F-test of whether specialty matters at all in comparison to intercept only. So what this is really asking is, if I just assume these are all the same, there'd be some amount of error. But instead I'm assuming they each have their own level. And is that any better? And here that says it's significantly better, in that that would have been unlikely. It would have been unlikely to get that much better just by chance if they really didn't have different means. So you might wonder, well, we have all these different options of contrast. What if I put a different contrast in? What if I did treatment coding and looked at this, the F statistic, it's 9.6. What if I did SAS coding? Well, it's the same. What if I did successive difference coding? It's the same. Helmert coding, same numbers. Sum to zero coding, same numbers. So all of these contrasts give you the same answer. And here's just actually random numbers that I'm just making up. And this even gives me the same number. However, not all contrasts you could come up with will come up with the same number. And you can see here's one that doesn't, and that's because Well, the degrees of freedom are different. And really, if you look carefully at this, you'll see that I've got two rows that are identical, 1, 0, 1, 0, which means I'm not really representing all three levels. I'm sort of recoding two of them as the same. That's a legitimate thing you might want to do. You might sort of believe that two levels of your variable are really not any different, so you want to treat them as the same instead of different. And you could come up with your own contrasts to code that specifically. Okay, so this, when we try to make predictions about an outcome based on a single categorical variable, that's called a one-way ANOVA. At least when we do the ANOVA test, when we do the regression, it's just a regression with a categorical predictor. And really there's almost essentially no difference between these, although many people don't even recognize that. So ANOVA is sort of a special case of linear regression, but if you, like some software packages, regression is an add-on that you don't get unless you pay extra for, even though ANOVA uses the same tools underneath it. Let's look at salary across these different values, and remember that some of the assumptions of regression are that we have equal variance in all the groups. And before we had to use some schemes, some measures, because to test this that were more about showing the how the variance of the residuals related to all the different levels of a continuous predictor. But now that we have specific categorical predictors, other tests are available for this. So here it looks like we might be in trouble, because it does look like the variance here might be smaller than this, although this, who knows, if this weren't an outlier, it might look very similar. But this variance looks a lot larger. So we would like to be able to test whether this is true, and test the homogeneity of variance assumption, and maybe find ways of dealing with it. So there's a lot of different ways to do this. One is called the Bartlett test. You can run the Bartlett test just with the same syntax as you run LM, or you could do it salary tilde, salary comma specialty, and you get the same answers. And here, it has a large value on 2 degrees of freedom, because there's two groups, or there's 3 different levels, and it says p is equal to 0.01. This suggests that you really do have different variances in the groups. However, some of these tests are sensitive to non-normality. So, do we have non-normality? We can check this, maybe, by looking at box plots, it's hard to see, or a violin plot. And this sort of indicates, well, these look pretty symmetric, but this looks pretty skewed. So maybe we really have non-normality, and it's not clear how to handle that in this case. Well, there's other tests that will check for difference that are maybe more robust to difference in variance that are robust to non-normality, like the Levene test, which is available in the CAR library. And so here, now this actually suggests that that they really aren't any different. Oh, you know what? I changed this contrast to be something that we don't want. So let's reset this before we do any of these, because specialty is now this degenerate contrast. Okay, so now that works. This doesn't change, but I'm guessing the Levene test will. So now this is sort of marginally significant. It says on 2 and 12 degrees of freedom it does this F test. It's 0.067. I wouldn't be highly confident in saying it's non-normal just because it didn't reach the 0.05 level. And so there's some sort of evidence for it being having different variance. There's also a non-parametric version of this, the Fligner or the Fligner-Test test, and this would suggest, it's right on the cusp of being significant, having significantly different variances. So what do you do in cases like this? Well, one way to do it is to do a test, just like the t-test has the Welch version, which doesn't assume equal variances. You can do the Welch's one-way ANOVA, which is embedded within the one-way dot test. So one-way dot test. You give a formula and data, and this will do a one-way ANOVA, but won't assume equal variance. It does the test sort of the same way it does the t-tests, by adjusting the degrees of freedom. So here we have this adjusted degrees of freedom, and here this no longer is testing the difference in the means. It's saying, well, we'll do the test assuming a difference in variances exists, and it adjusts this to compensate for the difference in variances, and says, oh, those means are different. So this would be instead of doing an ANOVA, we could do this. If we can set var.equal equals to true, and that's significant as well. It's even more significant, and that gives me the same thing as this would. These values, the f-test 9.622, 9.62, well, 623, 623. So the one-way test with the variances equal is the same as just a standard one-way ANOVA, whereas the one-way test by default is Welch's. It's called Welch's one-way ANOVA, I guess, and it doesn't not assuming equal variances. So that's one approach. We can also do a non-parametric test, and the most common non-parametric sort of equivalent of one-way ANOVA is the Kruskal-wallis test. And I think we actually looked at this a little bit when we were looking at non-parametric t-tests, but you can do salary tilde specialty. It doesn't give you any of the means or anything. It just does a test of whether specialty has any effect, and again, specialty has an effect here, but we're not making any assumptions about the variance or the distributions of the error noise. I could do it with tooth growth, and you can see here that tooth growth, the length of the tooth is significantly affected by this dose value. Okay, so just to be complete, we can also do one-way ANOVA tests with a Bayes factor, which is not really any different than what we did before, but we need to put it in a data frame. So we can do ANOVA Bayes factor and look at the results, and this will give me, well, specialty has a Bayes factor of 13.2, which is strong evidence in favor of specialty having an effect. There's some similar effects you can try. And we can look at, if we want to know, well, this is more getting into multi-way ANOVAs, but we can test for the effects of specific effects in the context of other ones by doing ANOVA. It'll give me all the submodels, and then picking out specific submodels. I can also then figure out the posterior distributions of these to do testing of specific comparisons, which I think we'll handle in the next section. Okay, so now if you manage to have a test, let's see, I think this is that maps onto your hypotheses. If you manage to set up contrast and they map onto your hypotheses, then you can just use the results of the linear model test to see if those particular differences matter. But generally we don't, and we want to make other tests. And so one way of doing this is to use just do all pairwise t-tests. And instead of doing that by hand, you can use the function pairwise t-test to do this. And this will give me all pairwise tests and say, well, here's the tooth growth. In each case, these are very small. So 0.5 differs from 1, and 1 differs from 2, and 0.5 differs from 2. But we worry, especially if you have a lot of these, that you might get a lot of false alarms. And so there has to be some way of correcting it. Now, the pairwise t-test function, by default, corrects this with a method called Holmes method. And so it adjusts the p-value that way. But other methods are available. Oh, and there's a whole sort of series of functions: Holm, Hochberg, Hommel, Bonferroni, BH, BY, FDR, none. So we could use any of these to adjust the p-values. So this is sort of oftentimes people will use the Bonferroni correction, which sort of assumes that all the tests are independent and makes you satisfy a much more conservative criterion. So we could do Bonferroni adjustment here with this, and we can see, oh, they're still all highly significant according to the Bonferroni adjustment. But another way to do it is if they're all planned comparisons, you should set up your contrast this way. Sometimes all of the comparisons are planned. You still have to worry a little bit about correction for over testing. But if you have a lot of different levels that aren't really planned, then some of those are going to be different, even though you didn't really care about them. And so if you just compare all pairwise things, you'll start finding things are significantly different according to t-tests, on average 1 in 20 times, even if there is no difference. And so you have to protect yourself. And once you do the ANOVA, the standard way to do it is to do an ANOVA and then do a post-hoc test. And one of the most, which does these all afterward. And when you do a post-hoc test, that tries, like these Bonferroni corrections, tries to correct for not having these hypotheses up front. So the Tukey HSD is maybe the most common one, and I can do Tukey HSD on the models, and it will show me these results. So these can be a little intimidating to look at, but this gives me, it tells me, does business differ from advertising? Does certification differ from advertising? And does certification differ from business? So none of this relies on the contrast we did up front. This does post-hoc tests, which requires sort of an adjusted p-value, and it tells me, oh yeah, these two differ, and these two differ, but these two do not differ. Similarly, we have this correction here. There is a alternative within the Agricole library called HSD test, which works kind of nicely as well. It gives you a little more information, and at the end we've got, here it says treatments with the same letter are not significantly different. So A, B, C, they're each significantly different. But here we've got, here for the salary by specialty, we have A, B, and B, which means advertising and certification are not significantly different according to this test. So these are both low, and this is high, and there's not strong evidence that advertising really makes more money than certification. They could make, it's likely that even if they made the same amount, you'd get a difference that big given the sample size we had. Okay, so that's sort of standard post-hoc tests. The approach for a Bayesian post-hoc test is actually in some ways much more intuitive. We just sample from the posterior, and then we can compare those distributions, and if they don't have a large overlap, we can say, well, they don't have a large overlap. We can look at the summary of these things, and this gives us the quantiles. So here we can see the means of the different quantiles, and this is all going to be with respect to the mean. So there's a mean of 36.7, and then this is very similar to that, I guess, sum to zero coding we had before, but now certification appears as well. You'll probably, I mean, because it's mean, you'll see that 12 minus 2 is equal to 10. So these, I don't know if these are going to be identical because of sampling, but there's a lack of constraint when you have a mean plus all the differences between the means. But so we can look at advertising and see, well, the 95% interval of advertising is between negative 10 and plus 5. The 95% interval of business is 2 to 21, and certification is negative 18 to negative 1. So you can see that like the 95% range of possible values between business and certification don't overlap at all, but advertising overlaps with each of those. So this tells a little different story. The most likely parameter values for advertising overlap a little bit with these other two, and we can't really be confident that that they are that different. And then a lot of times people will plot these post hoc as histograms on top of one another, or you can plot the densities here. You can see that, let me zoom in on this. This is what I was just saying. This would be, I forget which this middle one is, but there's very little overlap between these two, and so you might say, you might just give the percentage of overlap. But here there's considerable overlap, especially between the white and the red, and so your post hoc confidence in those being different is substantially smaller. You could also look at the number of times in which, you know, the one level is different than the other level. So 4 is different than 3. I guess 4 is going to be like, if we look up here, 1, 2, 3, 4. 4 is certification, 3 is business, and we can see that only 0.03% of the time was business, was certification higher than business in its post hoc. I'm sorry, in its posterior distributions. Here, 4 was greater than 2, 91% of the time, so maybe that's not really high confidence. And here, it's 97% of the time that 3 was greater than 2. So this is higher confidence. And you can, you know, report these specific numbers, and just that's sort of the end of the analysis, the post hoc analysis. All right, so that is it for this chapter, and it covered putting factor variables into linear regression, and then using that to test differences between levels in a regression, transferring that into an ANOVA, thinking about this in terms of an ANOVA instead of a regression, recognizing that regression and ANOVA are basically the same thing, and then looking at some tests, some alternative tests, including non-parametric and Bayesian tests, and finally looking at ways of doing post hoc tests, tests you didn't plan but can do after the fact to look at differences between particular levels of variable. In the next chapter, we'll look at using multiple predictors in a regression. Instead of a one-way, it'll be a multi-way ANOVA. So stay tuned.